Indeed. Yes. Thank you very much for the invitation. It is a pleasure to be here and give this sort of talk number 2. I'll share my screen and then make it go full screen, and then hopefully we're good to go. Okay, so I'll just. Okay, is that good for everybody?
Yeah, wonderful.
Excellent. Okay, so let's make a start. So this afternoon, following on from Tuesday's talk, the topic of this afternoon's presentation is modeling cancer invasion and metastatic spread. So Tuesday we looked at angiogenesis, specifically in terms of tumors, tumor-induced angiogenesis, and we briefly touched on the fact that solid tumors grow initially as an avascular multicell spheroid, roughly spherical, just like a blowing up balloon. And then the nutrients are just delivered via diffusion, and so there's a diffusion limited size of a few millimeters. We'll see that in a few slides' time. And then cells towards the interior, cells in the interior are necrotic, they're dead, but then there's a middle zone of cells which are hypoxic, and these cells were secreting the angiogenic factors, stimulating the growth of the new blood vessels, all driven by the endothelial cell dynamics. And then when the new vasculature connected with the tumor, that allowed the tumor to really grow in this it was vascularized, and then it grew in this vascular, it was a vascularized tumor which grew because of essentially the delivery of oxygen and other nutrients to it. And that has other implications, which we'll see in this talk for invasion and metastatic spread. So this is the overview of the talk. I'll touch explicitly in the beginning here on the hallmarks of cancer, and we'll find out, because I didn't really touch on that on Tuesday, we'll find out today that angiogenesis is a so-called hallmark. And then we'll focus on modeling cancer invasion. And cancer invasion is intimately connected to metastatic spread, and the two are linked through angiogenesis, so that's a nice connection there. And then we'll have some other applications. There's a in vitro assay called an organotypic invasion assay, and we've done some modeling with the sort of data from some work done by experimentalists to try and benchmark our invasion model, and then we'll talk about where we'd like to go with future work. So this is a famous picture image that a lot of us use in mass oncology. It's from the 2000 paper of Hanahan and Weinberg, The Hallmarks of Cancer, just often referred to as Hanahan and Weinberg. And in this paper, now cited tens of thousands of times, it's a very, very highly cited paper, Hanahan and Weinberg focused in on what they felt were the key differences between cancer cells and normal cells, and massive cancer cells, i.e. a solid tumor, let's say, and normal tissue. So they tried to distinguish between normal and cancer in a sort of minimal way. They had to they tried to get down to the key differences between normal cells, normal tissue, and cancer cells, cancerous tissue. And they came up with 6 things. 4 of these so-called hallmarks, these distinguishing features between normal and cancer, are really about what happens inside cells, cell signaling pathways, or secretion of molecules. So there's resisting cell death. That's normal cells undergo a process called apoptosis. After a certain time, they die. Cancer cells don't do that for various reasons, one of which is there's a molecule called p53, which is mutated and doesn't function properly. And they secrete signaling molecules which allow them to keep proliferating. They also evade external chemicals or growth suppressors, so the body tries to shut down by sending chemical signals to stop them proliferating. They've developed mechanisms to stop that, again through intercellular signaling pathways. And they have what Hanahan and Weinberg call an replicative immortality, so they just keep proliferating. So these 4 hallmarks are really at a cell or subcellular level. And the 2 other hallmarks they identified were inducing angiogenesis, so tumor-induced angiogenesis, and activating invasion and metastasis. So angiogenesis, as we saw, so angiogenesis and invasion metastasis, these are sort of macro-scale hallmarks, shall we say, and the other 4 are sort of micro-scale hallmarks. So the 2, angiogenesis and invasion metastasis, they are intimately connected, as we'll see. And why I became interested in invasion and metastatic spread is really that metastatic spread, i.e. secondary tumors, so metastasis is referring to the secondary tumors which are distinct in locations from the primary tumors. You can see here, this is a quote from the World Health Organization. And the last sentence there, metastases are a major cause of death from cancer. The fact that you have secondary tumors to treat makes it very much more difficult than if you just had a single primary tumor. And we can see that also in the original paper of Hanahan and Weinberg. You can see there in the middle, this is a quote about the hallmark invasion and metastasis. And as they say here in the middle of this paragraph, these distant settlements of tumor cells, metastases, are the cause of 90% of human cancer deaths. So basically, if cancers didn't spread, far, far fewer people would die. And so if you could stop cancer spreading, then by definition, far fewer people would die, and it would be easier to treat and perhaps localize the primary tumor. So, but once a primary tumor spreads, successful treatment and prognosis is very poor. Okay, so just then to touch explicitly on the growth of a solid tumor before it starts invading. So this is pre-invasion, and this is known as an avascular solid tumor because it has no blood supply. So this is also pre-angiogenesis. And this is some images of one of these multi-cell spheroids. You can grow them in a laboratory. They grow as nice little spherical masses. And because the nutrient is supplied externally and it's all via diffusion, so it's mainly oxygen at this stage, the growth stops at a few millimeters in diameter, and when the whole mass is composed of about 1 million cells. And so oxygen is being delivered to the tumor externally, and so the oxygen then diffuses into the tumor, and it's being depleted naturally. There's some natural decay of it, and also there's some uptake of the oxygen by the cells who are receiving the nutrient. So the concentration profile, it's high on the outside, and as you can imagine, it then decays away to lower levels in the interior. And below some thresholds, two things happen. Once it drops below a first threshold, the proliferating cells become quiescent, so they stop proliferating, but they're still viable. And then if the oxygen level drops further, the cells die completely, and you're left with an interior necrotic core. And so this cross-section here, the inner light region has been stained, and that's necrosis. And then this other sort of outer shell is composed of proliferating cells and quiescent cells. And this is a zoom into a slightly larger spheroid. And here you can see this is at steady state. There's a very thin proliferating rim, as it's called, of maybe half a dozen cells deep, and then the rest is composed of quiescent and necrotic regions. So that's if all tumors simply grew to a few millimeters in diameter, then that wouldn't really be a problem for people who had such a thing. You wouldn't really. In fact, at this size, it's not really. You're not aware that you have a small avascular tumor in your body, unless it was, say, on the surface. But inside, you're unaware. So two things happen. As we saw on Tuesday, the hypoxic cells can secrete tumor angiogenic factors, VEGF, and you can induce angiogenesis, and that leads to vascular growth. The other thing that can happen, either distinctly or connected to angiogenesis, is local invasion of the surrounding tissue. So something activates the cancer cells to start secreting enzymes. They're called matrix degrading enzymes. And so that allows the surrounding tissue to be degraded, and that creates opportunities, as we saw on Tuesday. We'll go briefly summarize that in a minute. So via haptotaxis again, so the cancer cells can interact with collagens and fibronectins in the extracellular matrix through adhesion, and so they can move with directed motion through haptotaxis. Also, they can proliferate and move into the sort of holes or the gaps that they've created. And so that allows them to spread locally into the tissue and not remain localized as a nice spherical or symmetric mass. So you get this very uneven spread down to local invasion, partly because the exterior is heterogeneous. So you don't just keep invading blow up as a bigger and bigger balloon. You start to develop this highly asymmetric shape with sort of fingers of columns of cancer cells penetrating into the matrix. And this has been known for a couple of thousand years. The ancient Greeks were aware of this. And in fact, the word carcinoma derives from the Greek word for a crab, as in fact does the term cancer. That's the Latin for a crab. So the ancient Galen and all these ancient medical practitioners were aware that cancer was not a good thing, and they described it in such a way that, because when they saw presumably people who had cancer and had died, and they looked into them, then they could see this very heterogeneous spread of cells into the tissue, and so that's why we've got the name. Here's an image of this is let me just see where it is. I think this, yes, so this is an esophageal cancer, so that's cancer of the esophageus, and this shows the stages of invasion getting worse. And on the left-hand panel here, you can see the deeply stained cells are the deep dark purple cells are the cancer cells. You can see here this light purple region is the sort of boundary, and then below here we have the normal healthy tissue. So there's a clear zone between cancer cells and the healthy tissue. And the authors of this paper, a Japanese group, they called this infiltrating pattern A. And they found that patients with this type of invasive pattern, probably they were caught at an early enough stage, they had a very good, they had a high a good chance of survival. So the prognosis for them was good. And that's basically because the cancer really hadn't become heterogeneous and invaded widely. There's a sort of medium pattern where there is still a demarcation, but there's a lot more heterogeneity of the cancer in the normal tissue. And then they also had a third class called infiltrating pattern C, and that's basically a heterogeneous mess. So it's very difficult to know where we have healthy tissue and cancer. Well, we have healthy tissue and cancerous tissue all mixed up. So it's very hard to then know where you would, for example, if you were looking to do surgery, it's very hard to know where you would actually cut to remove the tumor, so that you were sure that you'd removed all the cancer. So that's the overall biology of cancer invasion. So cancer cells interact with the extracellular matrix through the secretion of matrix degrading enzymes. So we have three main variables to focus on if we want to develop a mathematical model, and those variables are the cancer cells, the matrix degrading enzymes. They're secreted, they degrade the matrix, and then the cancer cells interact with the matrix through haptotaxis or proliferation into the gaps. So those are our three variables that we're going to produce a basic mathematical model: cancer cells of density C, matrix degrading enzymes of concentration M, and extracellular matrix of concentration V. And again, just to recap what we noted on Tuesday for angiogenesis, on Tuesday we had haptotaxis. That was down to the endothelial cells interacting with the matrix through secretion of these enzymes. And now it's the exact same process, except it's cancer cells secreting enzymes and interacting with the matrix. And so directed motion via haptotaxis. So this is the same slide you saw on Tuesday. We have cancer cells on a glass slide, so they can't adhere to it, so they stay all together localized in the center. When you put some matrix components in, they can adhere to the components and they start spreading out more widely. And then if you put a component of matrix that they get a really good adhesive grip to, they can spread very widely across the whole glass slide. And so that is happening in vivo in a real situation. when the cancer cells secrete the enzymes, they interact with the matrix components, and so the tumor doesn't remain localized, but spreads into the tissue, like we saw in the previous slide here with these invasive patterns. So if we have...
Can I ask a question before the model?
Yes, of course.
Yeah. How critical, how essential is this crab structure to what's happening after, like the invasion, the cell migration, and so on? If the answer is yes, that it is critical, and in dendritic cells and in other patterns in nature, the crab structure appears to be like favorite in nature. And if we understood this very well, maybe there is a way to lock the crab pattern, and then we are winning.
Yeah.
So I may be very naive in my very simple thinking, but before modeling this, maybe we have to understand that crab pattern very well.
Yeah, that's a very good point. I personally believe the crab patterning is down to various factors which happen as the cancer becomes progressively more malignant. So if it was simply to invade as a growing balloon, probably bad things would happen, but on a slower time scale, and then it's easier to deal with if you're just expanding as a big balloon. However, if angiogenesis takes place, then even if it hasn't explicitly invaded, if angiogenesis has taken place, then the cancer cells can access the blood system through the new microvasculature. So even if it hasn't really invaded very much, if angiogenesis then takes place, it can still have access to the blood system, and you can still then get metastatic spread. For this local invasion, obviously the cancer then is more proactive, and if the cells are explicitly spreading out into the local tissue, they're likely to encounter blood vessels, and we'll see that later on when we do the model of metastatic spread. So they're likely to encounter blood vessels, and then once they encounter blood vessels, they can then access and without angiogenesis. And if the two happen together, that's probably the worst scenario. But I think as the cancer ages, and the cells keep proliferating, more and more mutations happen. And one mutation that happens is that the cells lose adhesiveness. And that's down to something called an epithelial mesenchymal transition, which we'll see in a minute. And the loss of adhesion is what I think frees the cancer cells up to generate this crab pattern. So if you could deliver drugs which allowed the cells to stick back together again, or reverse this epithelial mesenchymal transition, which we'll touch on later, you may have a chance of localizing it in a more symmetrical shape. But the crab-like patterning is very that's a signature pattern of invasion.
Okay.
Okay, so a basic model that we can write down, just like our basic angiogenesis model, the tumor-induced angiogenesis model for our three variables, we simply, again, so there's a macroscale model looking at densities and concentrations. So we're interested in then just the interactions between the three variables, cancer cells, enzymes, and matrix. So we write down 3 PDEs with all the things that we believe are happening in the model. And so the cancer cells have some random motion. They have some haptotaxis in response to the matrix gradients, which we'll see how they're created. And of course, the green is how they're created. And then they're probably proliferating as well. The matrix degrading enzymes, they're produced by the cancer cells, and then they diffuse and decay. And then when they're produced by the cancer cells, they degrade the matrix. So that generates the gradients and allows the cancer cells to interact and spread via haptotaxis. The matrix may try and remodel and come back to a normal, healthy state, It may not, it depends, but you can put in a sort of remodeling term to put it back to where it was before the cancer cells were there. And this is sort of logistic growth, acknowledging the fact that the cancer cells in the matrix are competing for space. And now, if you know your applied math and your math biology, you'll see that this is a sort of modified Fisher equation. There's the haptotaxis, but more or less you would expect a kind of traveling wave solution for this model if you start off with some initial data that's sensible. However, you can make the model slightly more simple by, as we did with the angiogenesis model on Tuesday, initially ignoring cell proliferation. And this is because there are two main types of cells for invasion: epithelial cells and mesenchymal cells. And as we'll see slightly later in the talk, it's the mesenchymal cells that are doing the invading, and they don't proliferate very much, whereas the epithelial cells proliferate and don't migrate very much. So this is a sort of invasive model for mesenchymal cells. And I put this together essentially with Sandy Anderson. We had some help from some colleagues at the local hospital in Dundee, where I was at the time, Dundee University. And so you can ignore the cancer cell proliferation, and you can also, when you look at the data, the haptotaxis is much bigger than the cell diffusion. So this is a haptotaxis dominated system. It's like a hyperbolic system. It's tending towards a hyperbolic system for the hyperbolic equation for the cancer cells. And again, if you assume that there's no matrix remodeling, there's simply degradation of the matrix, then that makes our model as simple as possible. So if you then simulate that, and initially just in a one-dimensional domain, then you can put a tumor at one end of your domain. So that's our initial solid tumor. And this is the extracellular matrix that it's a way to try and invade. And then we have some initial profile of matrix degrading enzymes. And so as time evolves, the matrix degrading enzymes degrade the extracellular matrix. They create the gradient. And as we can see, because we don't have no proliferation, it's not a kind of standard traveling wave, but we found this interesting behavior that cancer cells, the tumor cells at the very front, at the leading edge, sort of broke away from the main tumors cells which were left here. They would move then slowly by diffusion, because diffusion is slow. And so this, in a one-dimensional setting, in a very qualitative way, might be the beginning of a localized invasion. And if you have this happening in a heterogeneous system in 2D, then you could get these columns of cells, cancer cells, moving into the tissue, just like we saw in the initial diagram of an invading cancer. But this is just a one-dimensional qualitative outcome. And so the next thing that we did, we put this into 2 dimensions, and we made our extracellular matrix a little heterogeneous, so it's not a uniform density. There's a difference in density from the start. And when you simulate this in 2 dimensions, you basically we were getting, again, qualitatively an invasive pattern that looked like those patterns we saw where we have heterogeneous spread into the tissue. So it wasn't just we started off, the initial conditions here were just a perfectly symmetrical distribution of cancer cells in the middle. So you don't just invade as a bigger and bigger 2-dimensional balloon. You do, in fact, get this heterogeneity as you interact with the matrix in different ways because of the matrix profile at the start. So qualitatively, we were capturing the dynamics that were observed both in vivo from the Japanese group and the classical pathology of an invading cancer. So the next step that we did, again, following the angiogenesis model, that's very nice at a macro scale, but the colleagues at Ninewells Hospital that we were working with at the time, they were really interested in trying to optimize their surgery. They were breast cancer surgeons, and they were trying to make sure that when they operated on women with breast cancer, that they didn't get recurrence of the same tumor, the same cancer at a later date. And a component of that, they felt, was that it's very difficult for them when they operate, it was very difficult to see exactly, as we saw in those infiltrating patterns from the Japanese group, it's very difficult sometimes to distinguish between cancerous tissue and healthy tissue. There's no just clear, it's called a visible margin. Sometimes there's no clear visible margin. And so basically it's a bit of guesswork and down to the experience of the individual surgeon. And if the individual surgeon is too conservative and doesn't take out enough tissue, and you want to do that because if you take out too much healthy tissue, that has other consequences for the patient. So it's a balancing act. So if you don't take out enough tissue, then some of the cancer cells may have gone into the healthy tissue and you've not noticed them. And so by removing the cancer, as you think, you've actually still left some cancer cells in the tissue, and those ones will still persist. And then in a few years or months or years' time, you will have the same cancer growing in the same location because you didn't surgically remove everything in the first instance. So we were interested then in trying to get a microscale model, an individual-based model, to try and predict the furthest distance that a cancer cell would move into the tissue. And to do that, we discretized the cancer cell equation as we had done with the endothelial cell equation we did on Tuesday. So the cancer cell equation is now discretized, and then we're working with the same PDEs for the enzymes in the matrix. And so we have this algebraic equation for the cancer cell at grid point ij. Again, it's on a two-dimensional domain at time point n+1, and that depends on the cancer cells at the 5-point stencil that we showed on Tuesday. And these coefficients, P0 to P3, are essentially, as we saw on Tuesday, this is an unbiased random walk with these Ds, and the biased random walk is coming through the discretized haptotaxis. So that's providing a bias to the motion. And that biases these numbers P0 to P3, which are proportional to the probability of movement on the 5-point stencil. Okay, so again, this is just a recap of what we talked about on Tuesday. This is the explicit finite difference approximation to our cell equation. These were endothelial cells on Tuesday, now they're cancer cells, and we're working on a 5-point stencil. And so the numbers P0 to P4 are just the probabilities of either remaining the same or moving to the local, the nearest neighbor grid points on our stencil. Okay, so we have now a hybrid model that we had on Tuesday. We're applied to cancer invasion. And so our cancer cells are individual cells on the grid points. And so they can move from grid point to grid point. And that's all controlled essentially by the haptotaxis interactions with the matrix. But now, because we've got a discrete model with cellular automaton-like components, as we had on Tuesday, we can add in things like cell proliferation, cell-cell adhesion, cell mutation at the individual cell level. So at a time step, a cell may have a probability of becoming more proliferative, and so it would proliferate more, or it would become more haptotactic, more adhesive to the matrix, and essentially move faster. So you can incorporate that into the model with sort of mutation rules at each time step. So again, by doing that, and then simulating the model on a two-dimensional grid with individual cells. So initially we have a clump of cancer cells in our matrix, and then over time, as you can see, we have this spread of the cancer cells into the extracellular matrix. And at a late, this is all non-dimensionalized, but at a late time here, you can see at the bottom right, you can see this is heterogeneous. It's not just a nice spherical circular pattern. You can see that it's heterogeneous. And not only that, for example, here there's an individual cell that's out, and here there's an individual cell that's moved out. And so there are some individual cells that have moved further away from this main central mass. And when we showed these simulations to our clinical colleagues at the hospital, they thought that we just photocopied them from a pathology textbook because this is exactly what they were encountering in their surgery. There's more or less a visible margin here, you could see that. And then there are these sort of rogue cells outside. So if you were a conservative surgeon, you would just cut these main cells, but you would be missing some of these cells on the outside, and then they potentially could continue on and create another tumor in at a later time. So the hybrid model allowed us to qualitatively show that individual cells could move away from the central mass, and you had a heterogeneous distribution in tissue. At that point, we were, again, as I said, similar on Tuesday, we were hoping for some real data. We were hoping to get a grant to allow our clinical colleagues to do some in vitro experiments. That never came off. So again, we just had to leave the model there as a theoretical exercise, and it was just needing some data if we could have moved that forward. But as I say, we just had to leave it and then move on to other things. And I picked up on this again some years later when I had a PhD student at St Andrews University, and she was interested in pursuing a PhD thesis on invasion and also metastatic spread. So we re-looked at the model that Sandy Anderson and I had put together and updated it with in the intervening 15 years or so, updated it with the additional biological information that had arisen in the intervening years. And there are two main aspects of the model that we focused on to update and improve. The first was to incorporate this so-called EMT. So this stands for an epithelial mesenchymal transition. So cancer cells, when they're invading, initially you can imagine from that multicell spheroid, they're linked together and they're connected via adhesion. That's the sort of that's the default for epithelial cells. They link together in sheets of cells or clumps of cells with adhesive bonds. But as a cancer becomes more malignant, those bonds are lost, and the epithelial cells undergo what's called a phenotypic transition to mesenchymal cells, and mesenchymal cells are more active in migration. Epithelial cells are more active in proliferation. So there's a switch between these two phenotypes. So we thought that we should incorporate that effect into the model. And then in terms of the matrix-degrading enzymes, in the intervening years, it was found out that in addition to the diffusible matrix-degrading enzymes, such as matrix metalloproteinases, there were also a new class which were called membrane-bound matrix metalloproteinases. So rather than being secreted by the cancer cells and diffusing into the tissue, these membrane-bound enzymes were secreted by the cancer cells, and then they were rebound to receptors on the surface of the cancer cell itself. So as the cancer cell interacted with the matrix, this membrane-bound enzyme degraded the matrix very locally, very close to the cancer cell surface, rather than diffusing and degrading. So this is a little schematic diagram of this EMT, the epithelial mesenchymal transition. And here you can see epithelial cells in their normal state. So they're connected together with adhesive junctions, and they're sitting on some kind of basement membrane, which is the layer between them and the extracellular matrix. As they undergo a transition to malignancy, they start to change their shape, they start to lose the adhesive bonds between them, and they start to degrade the basement membrane, allowing them interaction with the matrix. And then when they're actively invading, they become mesenchymal cells, where they're not proliferating, they're actively migrating and interacting with the matrix components, and that allows the local spread. So in order to incorporate that in the model, we thought we'd have two cell types rather than just one cancer cell. We'd have epithelial cancer cells and mesenchymal cancer cells. And the two equations would have to account for the differences between the two cells. And this is like a proliferate or migrate model or a go and grow model. There have been various models over the years that have focused on this aspect. And so the differences are that the mesenchymal cancer cells are more motile. They invade, they can invade as individual cells. They don't need other cells around them. And they can also intravasate. So that's the process of getting into a blood vessel, which is connected with angiogenesis, if there's angiogenesis involved. But if an invading cell encounters a blood vessel, then the mesenchymal cells can degrade the blood vessel outside and drill a little hole essentially, and then intravasate and get inside. That's the technical term for getting inside. And it's the mesenchymal cells that express these membrane-bound enzymes and also the diffusive enzymes. So they're doing all the action at the front. The epithelial cells, they don't express enzymes, and they really can't, they can invade, but they need to be in the presence of mesenchymal cells. So they're kind of playing follow my leader, if you like, whereas the mesenchymal cells are more or less independent, and they are the ones that are pioneering into the tissue. They are relatively static, although they can move slightly if they're in the presence of mesenchymal cells, but they also proliferate. So they can fill gaps by proliferation. So we needed to take into account these differences in the model. And we also needed to take into account these membrane-bound proteins. And this was first discovered in a very elegant paper by Stephen Weiss and his group in 2009. And they showed in this nice paper that it was really necessary to have the membrane-bound proteins for invasion. And they did that with a very nice experiment. They took multicell spheroids, and essentially they knocked out the possibility of the diffusible enzymes. So that they ran a control experiment where the cancer cells invaded, and then they knocked out the diffusible enzymes, and then they knocked out the membrane-bound enzymes, and they looked at the differences in the pattern. So this is their control experiment on the left-hand side. So we have an initial mass of cancer cells embedded in a collagen gel. So collagen is one of the fibers in extracellular matrix which the cells can adhere to. And so we can see after a few days, we have an invasive spread into the collagen gel. This central panel is where the diffusive enzymes were knocked out. So they engineered the cells to stop them secreting the diffusive enzymes, but they did have the membrane-bound enzymes. And you can see there's very little difference between this invasive pattern and the control pattern. And then in the right-hand column, they knocked out the membrane-bound enzymes, but allowed the diffusible enzymes to be present. And so you can see here that there's very little invasion at all. It's more or less the same as the initial condition. So the invasion really requires these membrane-bound proteins. The secreted enzymes can degrade the matrix and allow invasion, but they need to be activated by other chemicals. So that's more complicated. But these membrane-bound ones simply degrade the matrix and allow the cell to invade. So we updated our invasion model, and we have now two populations of cancer cells. We have epithelial cells, and so they diffuse and have haptotaxis. And we're going to discretize this and add in proliferation at the appropriate stage. So this is the PDE first of all. And then we have our mesenchymal cells. They diffuse and have haptotaxis in respect to the matrix. We also have the diffusible enzymes, but as we noted, they're only secreted by the mesenchymal cells. So we have a production term related to the mesenchymal cells. They diffuse and decay. And then the extracellular matrix, we're accounting for the membrane-bound by this additional term. So we have diffusible enzymes that are degrading the matrix, but we have the mesenchymal cells explicitly degrading the matrix on contact. So rather than go into a further level of modeling with receptors on the cell surface, we just assumed that when the mesenchymal cells connect with the matrix, they can degrade it through direct contact because they have these membrane-bound enzymes on their surface. So we now discretize the two cancer cell types. So we have a discrete system for the epithelial cells and a discrete system for the mesenchymal cells. And then once again, at the discrete level, we add in these cellular automata-like rules for the cells. So we allow the epithelial cells to proliferate, for example, and the mesenchymal cells not to proliferate. To proliferate very, very slowly. We allow the epithelial cells to migrate, but very, very slowly via haptotaxis, whereas the mesenchymal cells interact strongly via haptotaxis. And so we add in the discrete rules as in our original model. Okay, we then benchmarked the system against the experiment of Weiss and his group. So this is the control experiment. Then we knocked out the diffusible enzymes and allowed the invasion to occur only by the matrix membrane-bound enzymes. And then we knocked off the membrane-bound enzymes, and so we have a very good match with our parameters in our model to the basic control experiment. So with that benchmarking, the model parameters of invasion were fixed. Okay, so we can run some simulations there and get an invasive spread of the cancer with epithelial mesenchymal cells. It's kind of similar to the initial invasion model, except the mesenchymal cells are more or less at the outside and the epithelial cells are in the inside. And we'll see that just shortly. But then we wanted to focus on the metastatic spread component. And to do that, we have to look at what happens when these invading cells interact with a blood vessel that's in the tissue. So we're not going to consider angiogenesis, although we could, but we'll just consider healthy blood vessels in the tissue. And so when the cancer invades, if it encounters a blood vessel, then they interact and go through a series of events. First of all, we can have intravasation. So if a mesenchymal cell interacts with the blood vessel, it can intravasate, and then it can get into the blood system. If there are some epithelial cells connected to mesenchymal cells, that group can also get into the blood system. Once that group of mesenchymal epithelial cells are in the blood system, they split up into individual mesenchymal and epithelial cells, and then they're carried throughout the blood system. There's a probability of survival in the blood system, which you can get from the data, in experimental data. And then at some distant site, you have the reverse process. It's called extravasation. So individual mesenchymal cells can stick onto blood vessel wall at some distant site or secondary organ, and then they can do the reverse process. They can squeeze back out from the blood system back into the new tissue, and then they can set themselves up as a new cancer. Or you can get the clumps of epithelial mesenchymal cells coming together and extravasating as a little clump of mesenchymal epithelial cells joined together. So there's some good data showing the relative probabilities of these events happening, and so that was incorporated into the model at the discrete level. And then our basic framework for the metastatic spread was to have a multi-grid system, a multi-spatial grid system. Rather than work on one grid where the primary tumor was, we had other grids in our model, and we transferred cells from grid to grid as they would in metastatic spread. So, and this is schematically shown here. We have a primary grid, which represents a primary breast cancer. And then we have, in our original model, we have 3 secondary spatial grids, which refers to spread to the lungs, spread to the liver, and spread to the bone. And we can parameterize the model with probabilities through, there was a nice study done of over 4,000 patients with breast cancer, and they were tracked with where the primary breast cancer, where it spread to, and so it spread to a number of organs, but the main ones were lungs, liver, and bone. And so we took that data and made probabilities of spread of our breast cancer cells, a probability to go to the lung, a probability to go to the liver, and a probability to go to the bone. So that was from real data on a big study that was carried out in 2013. So then we have to add these additional features into the model. We have the basic invasion model, but we have to add in intravasation and extravasation. We have to add in some blood vessels. We have to look at what happens in the blood system as the cancer cells are being put through the blood system. And then we have to add in the metastatic spread. And all that's essentially done by probabilities. Okay, so here's our primary grid. This is the grid in the breast. And here's our primary tumor composed of epithelial and mesenchymal cells. And rather just let it spread into extracellular matrix, we've put these are just random locations. We've put some blood vessels. So these are denoted in red. And we have healthy blood vessels. And we also have some leaky, poor, ruptured blood vessels that we all have in our body, and the interaction with the cells in ruptured vessels and standard vessels are slightly different, but we can just include that in the individual-based model. And so a flow chart, a schematic of what the individual-based model does is that we have the primary grid, so that's our breast cancer. We allow the epithelial and mesenchymal cells to invade via the discretized PDE system that we have through degradation of the matrix and proliferation. And then once a cell interacts, once an invading cell encounters a blood vessel, we then ask, can intravasation occur? And that's a simple probability. So if intravasation occurs, then we put the cells in the virtual blood system, so to speak. If intravasation does not occur, then invasion carries on at the next time step. If we put a cell into the virtual system, we ask ourselves, does that cell survive the journey in the vasculature? And again, that's down to a probability, and that's taken from experimental data. If it doesn't survive, then we simply just kill the cell and that's removed. If it survives the journey in the vasculature, then we allocate that cell into a secondary grid and we allow it to extravasate. And then once it's in the secondary grid, it can start to create a secondary tumor, either by proliferation if it's an epithelial cell, or it starts to locally spread and invade by if it's a mesenchymal cell. So in addition to our local invasion on the primary grid, we have these essentially probabilities, and that allows us to move the cells from the primary grid into the secondary grid, capturing the transition in the blood system through these probabilities and survival, and then the probability of extravasation and the probability then of moving into the secondary organ. Okay, so the next few slides I'll just skip through briefly because I've explained them in the previous 5 minutes or so. So we have a number of blood vessels on the spatial domain. Cancer cells interact with the blood vessels with a probability. They either intravasate or they don't. If they intravasate, then there's a probability of survival. They can intravasate as single mesenchymal cells or groups of mesenchymal and epithelial cells. And once a single or group is in the blood system, there's a probability of survival. And then, so this is a travel through the vasculature, so that's essentially a survival probability. And then we have a probability of extravasation of either the single mesenchymal cells or these groups, small groups of mesenchymal epithelial cells, and then they're put onto the secondary grid and start the process again. Okay, yeah, and if they manage to get to the secondary grid, then they behave according to the original invasion rules. They secrete enzymes, they have membrane-bound enzymes, and they locally invade by the proliferation and migration. Okay, so this flow chart here is what's happening for this metastatic spread. Primary tumor, invasion, cells interact with blood vessels, they survive the journey into the blood system, and then they extravasate into a secondary site and start the whole process again. Okay, so here's our results, and this is the results on the primary grid. So we have our epithelial cells on the first row, mesenchymal cells on the second row, the diffusible enzymes on the third row, and then the extracellular matrix density on the final row. So it's probably best to focus on the first two rows, the epithelial and mesenchymal cells. And as you can see over time, this is the initial conditions, over time we have invasion. The epithelial cells, because they're only really proliferating, they remain largely in the center of the domain. Okay, they don't really, they spread via proliferation, well, they increase via proliferation. And the mesenchymal cells, you can see they've managed to get to a greater extent. And then at later times, you can see the mesenchymal cells are more of them are at the outer edges of the domain, and the mesenchymal cells are sort of inside the mesenchymal cell envelope, if you like. And at this stage here, we've interacted with a number of blood vessels in the domain, and so there's a probability that these cells will have then been transferred to the secondary grids. And then that's exactly what we can now look at. Here is what happens in our lungs at an relatively early time in the process. we can see epithelial cells appearing in the lungs. This is a lung grid with random blood vessels on the lung grid. And then the mesenchymal cells appear at a later stage. And so once the epithelial cells get into the lung tissue, they simply proliferate. So they proliferate and create a little mass there. And then there's a bit of extravasation into this region here. And then that brings along some more mesenchymal cells. And then the whole invasion process carries on in the lungs. If we look at the bones at an early stage, they take longer to metastasize to the bone, so there's not anything happening in the initial early stage, but at a later stage, we can see the appearance of some epithelial cells and also some mesenchymal cells. And again, that would continue to invade if we can continue the simulations. And then finally, for the liver, spread to the liver is even slower than the bones, so there's nothing at an early stage. And at a later stage, you can maybe just see down here, there's a small group of mesenchymal cells that have extravasated out of this blood vessel here. And again, if we leave the simulation running long enough, this will carry on and you will get secondary formation in the liver. Okay, so the results that we managed to get with this basic invasion metastasis model were qualitatively in agreement. We could have a primary tumor and that would spread to secondary tumors, and that connected with the data we had from the study of the 4,000 breast cancer patients. And the speed of invasion was also in good agreement with in vitro experiments that had been done in certain invasion assays. So there was not just qualitative agreement with the mechanism of invasion and metastasis, but there was some quantitative agreement as well as far as we could get to the data. Okay, and then that was published a few years ago in the Bulletin of Mathematical Biology. The basic, we called it a framework for metastatic spread. And then subsequently, we've developed things a bit further. One nice thing mathematically that we've done is rather than just simply discretize the PDE and have things moving with probabilities, we've done a formal hybrid model with PDEs and stochastic ODEs for the individual cells. So rather than discretize and allow the cells to move by probability, we've discretized and allow the individual cells to move with a stochastic PDE, a stochastic system that more accurately represents their movement. And we also have a nice mapping between the PDE and the discrete system. It's a more formal mathematical way of doing it rather than a discretization. And with this formal mapping from the density model into the discrete PDE, we can also do the reverse mechanism of, it's called MET, mesenchymal to epithelial transition. So we can turn mesenchymal cells from invading cells into epithelial cells, which are just proliferating. So we can both incorporate EMT and MET into the model. And we developed that a bit further by trying really to connect with real data from an in vitro setting. So this was published just a couple of years ago. And this was a three-dimensional model connected to some data from one of these organotypic invasion assays. So this is the experimental setup. You have a collagen gel. So this is a three-dimensional, this is like a Petri dish, this is a cross-section of a collagen gel. And on the top of the collagen gel, you have some cancer cells. And you then expect the cancer cells to interact with the collagen and essentially invade into the collagen gel. And so that's exactly what happens. I think this is day 3, nothing much is happening. And then at day 9, you have invasion into the gel. And day 14, you have you can clearly see that the cancer cells have invaded relatively deeply and as little islands or patches of cells. They don't invade in a homogeneous wave of cancer cells. You're already getting this heterogeneity into the collagen assay. Here are some other experimental images from a slightly different line of cancer cells, but it's the same collagen assay. So over time, you can see that we have invasion into the assay, and it's very heterogeneous, rather like those infiltrating patterns we saw at the beginning. So we don't get we do get an initial invasion, which is, you might say is homogeneous, but definitely islands of cancer cells have broken off and have invaded the matrix more deeply. Okay, so when we incorporated this into our updated model in a three-dimensional domain with the formal transition from the PDE to the discrete system, then we got very good agreement with our model and the experimental data. So we have invasion of the cancer cells in little localized islands, and that's down to this epithelial mesenchymal transition and then a reverse mesenchymal epithelial transition. And here's our full three-dimensional simulation. And we compared that with the real data. If you look at the paper we published, we've done an explicit comparison with the experimental data, and this is a very good match to the real data. So this is a full three-dimensional simulation in a tissue of, I'd have to check the dimensions, but it's I think it's like 1 millimeter by 1 millimeter cubed. Okay, so for the future developments, we'd like to carry on with the modeling there and refine it further. And we'd like to create this hybrid framework for the metastatic spread and look into some more detailed PDE to stochastic differential equation modeling and develop a three-dimensional metastatic spread model. And then if we can, this is just a sort of computational exercise, either link it with an angiogenesis model. The last slide I showed on Tuesday was the vascular tumor, where we had the blood vessels growing down, they connect with a tumor, and then they interact with the tumor, and they have this heterogeneous growth of the tumor. So we could do that with this model. And we're also trying to put some more biomechanical realism in through individual-based force-based models. So rather than just have the cells on nearby grid points, if we have some biomechanical repulsive model of individual cells, then that's a more accurate description of what's happening at the individual level. And that would allow us to model cell-cell adhesion in a more accurate way. And then just the last few slides. Recently, we've revisited the biology, and unsurprisingly, the biology is a little more complicated than as it always is. The epithelial mesenchymal transition isn't just a simple binary transition from epithelial to mesenchymal. Biologists believe there's more of a spectrum, so it's like a continuum between epithelial and mesenchymal cells, and so you don't just go from E to M, you go across a spectrum of EMT. So you can have some partial cells which are, a combination of epithelial and mesenchymal characteristics. This is some data from breast cancers where they have tried to look at the phenotypes of epithelial mesenchymal cells. And so very recently, just this year, we published quite a detailed paper that I would have to spend a whole hour on. This is a paper where we have used non-local kernels to model the transition from epithelial to mesenchymal phenotype. So there's a parameter which determines where you are on the EMT spectrum. And so we have some now non-local models. This is now just computationally more complicated. And my colleague Nikos Fakianakis has done all the nice numerics to look at this non-local EMT transition. And when you do that, our computational simulation results, we could have a generic invasion model which invaded sort of heterogeneously. And then if we tweak the phenotypic parameter and make things a bit more mesenchymal, for example, we can get an invasive spread where we have these little islands of cells breaking off from the main body. And that's, again, connects in a nice way with the data that we saw both in that, the organic typic assay, the infiltrating patterns, and the previous slide of the breast cancer spread. We have little foci of mesenchymal cells further away from the main epithelial mass. Okay, so that was published just this year in Journal of Computational Science. So all the modeling details are there, and with additional computational simulations. And then We've also recently published this year a three-dimensional metastatic framework. So we have a three-dimensional primary tumor, and then we have secondary grids, which are three-dimensional domains of tissue, and we're now able to simulate a three-dimensional primary tumor, which grows, invades, and spreads through EMT, as we can see there in the first column. And then we have three secondary grids, which are three-dimensional domains of tissue in three different organs. And then you can see in these organs at later stages, we have the metastatic spread into the secondary organs. And if you can, this is just a little movie. Here's our primary tumor located in our first organ. And then this simulation, you can see the metastatic, the metastases are growing in, first of all, in organ 3, and then organ 4, organ 2, and then they also get to organ 5. This is a primary tumor with 4 metastatic secondary sites. So that's just a little insight into what we're pursuing at the moment. So we are trying to produce this full three-dimensional metastatic spread framework, and there are some inspirations out there. This is Alfio Quartarone. He's essentially created a virtual heart, and they're trying to pursue that to try and improve cardiac treatment, stop people having heart attacks, or treat people better who have heart attacks. And they have created a really beautiful three-dimensional heart with all the fluid flow and all the pumps and all the chambers and all the biomechanics. And so it's a really beautiful piece of work. So that's what we are really hoping to do over the coming years with our metastatic spread model, generate a framework that would allow clinicians to make better predictions for patients and allow them to make their clinical decisions at an earlier stage or make better clinical decisions. And so I would just like to finally thank two main colleagues on this work. The first is Linnea Franson, who did the original PhD with me on the original invasion model and metastatic spread framework. She's now in Roche Pharmaceuticals in Basel in Switzerland, doing great stuff and leading a modeling group there. And my colleague from St Andrews, Nikos Sfakianakis, who has undertaken all the excellent numerical work that allows you to take your nice conceptual model and translate it into real simulations connected to the data. Okay, and with that, I will stop, and I thank you for your attention.
So yeah, thank you very, very much, Mark. Wonderful. Another tour de force of mathematical modeling. I have a question myself. Maybe I'll ask it directly.
Yeah.
Hanin wrote papers on metastases, and he showed using stochastic modeling